Thank you for sitting down in front, Chef. The auditorium always fills from the back to the front.
Yes.
It's like people are afraid of the speaker.
You know, we complain about our students, but some of your colleagues are just
Oh, they're already. Oh, speaking of which, I'm going to turn my phone on.
Oh, yeah. It's a good reminder.
Well, of course, if you want to teach, you have to keep it in the. We got a postdoc.
If you need to know the time, there's a big red clock right there.
Oh, yeah. There it is. Great.
And it's a missed clock,
Mm-hmm.
so it's going to be really accurate.
Accurate. All right.
The only thing that controls its accuracy is like the speed of light between the mist.
Can't get better than that. Mm-hmm.
Well, good afternoon. Welcome to the Physics Colloquium today. Our speaker this afternoon is Tiffany Shaw. Tiffany's going to be talking to us today about the jet stream and climate change. Tiffany's title's up here. Tiffany's a professor in the Geophysical Sciences Department at the University of Chicago.
Use the mic. They're not going to be able to hear.
Oh. Generally, I think that's a good thing. So, Tiffany's a professor at the University of Chicago in the Geophysical Sciences Department. She received her PhD from the University of Toronto, which is a physics department that also does geophysics, okay, and climate physics. So Tiffany graduated there and took a job initially at Courant Institute and then Columbia University, and then moved on to her current position at the University of Chicago. Tiffany's won essentially every junior faculty award you can win, including the NSF Career Award, a Sloan Award, a Packard, and has won some prizes that aren't for junior faculty, such as the Horton Prize and also the very prestigious McIlwain Medal of the American Geophysical Union. So today, please join me in welcoming Tiffany to University of Colorado.
Thanks, Mike. All right, thank you, Mike, for the kind introduction. It's a real pleasure to be in a physics department today to tell you about some of our work in climate physics, looking at jet stream winds under climate change. This work has been done in collaboration with my former student, Osamu Miyawaki, there it is, who's now an ASP postdoctoral fellow at NCAR. And the subject of the talk is illustrated by this nice image I got from earthnullschool.net, where at any given moment in time, you can go to this website to see the wind patterns, temperature patterns, pressure patterns on the full sphere. But we're zoomed in here over North America to show a record-breaking jet stream event that's indicated by the very white colors. This event was in 2019, and it not only broke the record for the jet stream wind speed on that day, but it also led to a record-breaking cross-Atlantic commercial aircraft flight from New York to London. So before I get into the details of the jet stream, I want to make you aware of a APS topical group on the physics of climate, of which I'm a member. Our objective in this group is to advance and promote the knowledge concerning the physics, measurements, and modeling of climate processes. We do many things in our group. We have a newsletter, a Zoom seminar series. We also organize a session at the APS March meeting, which just took place in Las Vegas. I would be happy to talk to anyone interested in joining this, or if you need more information, please don't hesitate to reach out. All right, so let's get started with the topic at hand. The topic today is the jet stream. And for those who don't know, I thought I would start with this video from NASA, which shows the jet stream, which occurs at about 7 to 16 kilometers above our head. What we're looking at is very fast winds. 60 meters per second is the red contour that really clearly encircle the southern hemisphere at all longitudes. In the northern hemisphere, you can see it's very variable. It comes and goes. And as we zoom in on North America here, we see these very beautiful undulations of the jet stream that would be a subject of a different talk that we call Rossby waves. So why do we care about the jet stream? It's, as I said, 7 to 16 kilometers above our head. Well, there's a number of reasons why we care about the jet stream. One of them is that it controls the speed and direction of propagation of weather systems, such as shown in this image from Weather Underground. So these weather systems move from west to east because of the jet stream. It turns out if we were to examine them as perturbations to our equations, we would find that their intrinsic phase speed is from east to west. So these weather systems are guided by the jet stream, and they bring all of the weather that we are familiar with right now over Chicago. It's almost exactly this setup where we have this huge Gulf moisture surge. Northward, we're having a severe weather outbreak this week in Chicago in the Midwest, and that's certainly a function of the jet stream's pattern that we currently observe. This also leads me into another reason that we care about the jet stream, is when we look at the ground for really impactful weather events, like severe weather, whether that be just severe thunderstorms or tornadoes, we can often find that coincident with very fast-moving jet stream winds. And so why is that? Well, as the winds converge into a local fast region called a jet streak, and they diverge out of that region, it's coupled through conservation of mass to up and down motion. And that upward motion is very conducive to organizing and leading to convection, which is one of the key kind of large-scale ingredients that we need to get these severe weather outbreaks. So the jet stream doesn't just impact us on the ground through weather. We can also be impacted when we are in the jet stream, and of course we do that whenever we travel in commercial aircraft. So when we travel, especially when we're doing transatlantic travel, the pilots are always looking for where the jet stream is, what is its intensity, how can they maximize the tailwind to reduce that travel time between the two continents. So they often look for jet streaks, these regions of fast-moving winds that they can get the boost of the tailwinds. Of course, only in one direction. My travel to Chicago on the way home will be about 15 minutes less long or quicker because I'll be moving in that direction. But it turns out that it's not all fun and games in the jet stream. The jet stream can also change its magnitude at different altitudes, and this can lead to what you may have heard announced by the pilot on your commercial aircraft as rough air. We refer to this scientifically as clear air turbulence. And so when the jet stream changes how fast it moves as a function of altitude, it changes the forces on the aircraft and it leads to this rough air. And so for all these reasons, among many others, we would really like to understand the jet stream. We would like to understand how climate change impacts the jet stream. And so we can go on Google or ask ChatGPT, and for Google we get images like this, and it's suggesting some changes to the jet stream under climate change. But of course we ask, there are no observations of the future. Where does this information come from? How can we know about the jet stream in the future under climate change? Well, obviously the only thing that can tell us anything about the future with any fidelity is an actual physical model of the jet stream, where we can use initial conditions and boundary conditions to predict the future. And so that's what I want to start with in this talk. Before jumping to the climate change, I want to get everybody on the same page as to the physics that underlies why the jet stream exists. And once we have that under our belt, what we can do is then understand what might happen under climate change. Go ahead.
Yeah, I missed a couple of numbers.
Sure.
So, like, how high is it?
7 to 16 kilometers.
And
So,
what's the, like, is it a sheet that's, like, over some range?
so that's the altitude range that it covers, and then the latitude range is about 20 to 60 degrees latitude in both hemispheres.
But what I mean is, like, how thick is it in the altitude?
Yeah, so 7 to 16 kilometers.
Oh, that's the range.
That's the range, yeah, yeah. So the ozone layer is in the stratosphere, which is the layer that's about, 20 to 50 kilometers, so yeah, above. Right. And there's a whole different talk that can be given on how the ozone hole is known to affect the jet stream, but if you're interested in that, I'm happy to provide references. So, what do we need to do to understand the jet stream? Well, it turns out we just think of it as a physical system. This is just classical mechanics. We're going to bring to bear Newton's second law applied to the atmosphere as a fluid and ideal gas. Okay, so all very familiar to all physicists in this room. Of course, all we're doing is the usual F equals ma, but you know, one additional layer of complexity here is we're on a rotating reference frame. Okay, so the Earth rotates with angular velocity omega. We have three components of spatial components, so longitude, latitude, and radial distance. Consistently, we have three components of the velocity or momentum. East-west in this talk will be u, north-south is v, and up-down is w. Okay, I'm not going to get into too much math, and hopefully you'll be able to follow. I'll do some, color coding of all the forces that we have to consider when we are thinking about what can lead to a net acceleration of the air. I think all of us would have expected the gravitational force to be important. Obviously, that acts in the vertical or this radial direction that we defined. One that is potentially not familiar to you is a very important force for the atmosphere that we call the pressure gradient force. This is the differences in pressure that lead to air accelerating from high to low. So that'll be something that applies both in the vertical and in the horizontal. And then because we're in a non-inertial reference frame, we have to account for these fictitious forces such as the Coriolis force. And this is really the dominant fictitious force. We don't think too much about centrifugal force. So as any, I think, good physicist would do, we would start to consider in each cardinal direction, but here just vertical and latitude, what are the dominant forces that are going to be acting on the air that we can use to build a physical model, a leading order model of the jet stream. Well, the dominant balances in the vertical is actually static balance. The gravitational force is balanced by the net effect of pressure. And so, in a very simple free body diagram, we're just envisioning in this height latitude domain that the force of gravity pulls down and the net effect of pressure is to balance it in the vertical direction. This is a stationary balance, so it doesn't involve any vertical momentum, and it applies over very long horizontal length scales, which is exactly what we observe for the jet stream. It encompasses 1,000 kilometers, if not more, if we're in the southern hemisphere. And so when we look at our equations of motion, we neglect a bunch of terms, and what justifies zooming in on this force balance is this aspect ratio being very small. The vertical scale of the atmosphere, where 90% of the mass resides, is 10 kilometers in height. The horizontal coverage of the jet stream, as I've argued, is like 1,000 kilometers. So in this particular case of the jet stream, as a phenomenological thing that we observe, this is a shallow atmosphere or a small aspect ratio approximation. The atmosphere is like a credit card. It's very vertically shallow but very horizontally expansive. Now this balance, I think if you have heard of it, of course it also applies in the solid Earth, tells us something very fundamental about pressure. It tells us that pressure decreases exponentially with height. And it depends, however, that exponential decay on how warm and dense or light the air is. So if we have a very warm and light fluid, the exponential decay is very slow. And the E-folding scale height, which is to say how far you have to go in the vertical to have an e to the minus 1 decay of surface pressure, is very deep. However, if you're in a very cold and dense fluid, then the pressure decays exponentially very quickly, and that distance of the E-folding scale height, we call it, is very shallow. This will be something important as we build our model for the jet stream that we'll come back to. So that's the vertical. What about the horizontal? Well, obviously in the horizontal, the gravitational force to leading order, we don't need to think about it, and there's a force balance then between the fictitious Coriolis force and the pressure gradient force. So we flip our free body diagram on its side, and now we have the force balance in the latitudinal direction, y, between the Coriolis force and the pressure gradient force that we call geostrophic balance. And one of the first things you learn as a physicist when you go at least into atmospheric and climate sciences, there's a lot of terminology, a lot of jargon. And so just like for hydrostatic balance, to assume that these are the two dominant forces, we have to have neglected a bunch of other things. And what justifies us to do that, in this case, is what we call the Rossby number, where we take a measure in this non-dimensional number of what is the relative acceleration, whether it's the time tendency of the wind, which is an acceleration, or we measure the acceleration due to the fluid moving and advecting momentum along with it. That measured in the numerator, we envision its magnitude relative to the Coriolis force. And if this non-dimensional number is small, this is when the balance of geostrophy applies. Yes?
Is the pressure gradient force always opposed to the Coriolis?
In this horizontal direction, yes. And so let me move to the next slide and give you kind of a very simplified example of how we would envision this force balance manifesting through this sort of very simple 5-stage process. So we always think of the pressure gradient force as, existing. The Coriolis force doesn't always occur. It needs to it's proportional to the motion. So if we're not moving, we don't have any Coriolis force, or if the air is not moving. And so we always envision thinking about isobars. So these are lines of constant pressure. And the pressure gradient force in this diagram is pointed toward the north here with the cardinal directions. As the air accelerates starting from stage 1, the Coriolis force then grows because it requires motion as well as the Earth's rotation. It grows in magnitude until it's equal and opposite to the Coriolis force, and then we have uniform motion as a result, which is the wind. Okay, and an amazing thing that's predicted from this very simple balance is that the wind will be parallel to lines of constant pressure, or isobars. And when we look at weather maps very high above the surface, so away from the influence of friction, this is exactly what we see over large spatial scales, that if we can find the isobars and we look at the wind vectors, that the wind is blowing parallel to isobars. Okay, so what we want to do now is tie it all together. And that's really the two ingredients we need. We'll bring them together to reveal this leading order picture, physical picture, mechanistic picture for the jet stream. So we're going to start in the same domain of altitude and latitude, and we're going to envision at the surface and also in the atmosphere toward the equator, the air is warm and light. And that's because for all days of the year, there's sunlight shining at the equator. In contrast, toward the pole, half of the year there's no sun. And so this means that on average, as we move toward the poles, the fluid is cold and dense. So this gives us a starting point to look at the pressure gradient force. It points from high to low pressure. As the air accelerates in that direction, of course it's then deflected, in this case to the right in the northern hemisphere. And so the wind, that uniform motion that results, is into the page. It's negative, which is westward wind, this U component in longitude. Now, in order to infer what's happening at higher altitudes, which is where the jet stream exists, we have to make use of that hydrostatic force balance. And we previously argued that where the fluid is warm and light, the pressure decay exponentially is very slow. Whereas in the regions where the fluid is cold and dense, the pressure decay is very quick. And so the consequence of that is that the anomalous pressure pattern flips. Relatively speaking, the pressure is higher here over the equator than over the pole. And so that flips all of in particular, the force balance here for the Coriolis, where we have, for geostrophy, where we have the pressure gradient force moving toward the north. The air accelerates, it's deflected, just like it's on a merry-go-round that is moving counterclockwise. And so we infer this fast-moving eastward jet stream that occurs at these higher altitudes. And it's really this fairly simplistic picture, although acknowledging it does require one to think about these force balances in detail, that allows us to understand there's two fundamental ingredients for the jet stream. One, you have to have air masses of different densities and temperature next to each other. And two, you have to be on a rotating platform, in this case, Earth being that. Now, if we know those two fundamental ingredients, what we can do is combine them even in an even simpler setting, which is this sort of great set of experiments that they developed at MIT called a weather in a tank. You take a cylindrical tank, you put it on a rotating platform, you put an ice water bath in the middle, and you fill it with room temperature water. Then you turn on the rotating platform so that it's rotating around. And what you find, in order to visualize this, you add dye, in particular green dye, to visualize the fluid in the interior, and this purple potassium permanganate crystals which sink to the bottom and trace out the flow at the surface. You can therefore simulate in this very idealized tank setup those two ingredients, rotation and temperature contrast, to generate a jet stream. So we can now ask, what do we see emerging in the observations, having built this physical picture? Well, when we go to that upper level of the jet stream now, around 10 kilometers, and this is measured in pressure units because pressure decreases exponentially monotonically with height. So we typically look at the jet stream around this 200 hectopascal level, and we look at our best known state estimate, our best known observational estimate of the winds at that level. This is for a particular time period, and from a particular data set, which is not a pure observation. Our best known state estimate comes from what we call reanalysis data, where we combine a model, physical model, of the atmosphere constrained by observations through data assimilation. This gives us a four-dimensional state estimate. And when we look at those data, we see this fast-moving jet stream. On average, this is the mean in both hemispheres, and a large fraction of this can be connected to that thermal wind. There is some role for momentum transport and generation of the jet stream winds by those weather systems that have that north-south motion, which we didn't build into our thermal wind, but it's a second-order effect that we're not going to get a chance to talk about today. So now that we've got this foundation of understanding, we're going to move back to this question about the future. The fact of the matter, again, is we have no observations of the future. And so what climate physics can do for us is allow us to make predictions. And so when we're interested in going from today to very end of century, we can't rely on statistical extrapolation or even machine learning algorithms trained on modern observations, because far into the future we're very out of sample under global warming or anthropogenic climate change. And so what we rely on, of course, is our understanding of physics applied to the climate system, which is a set of nonlinear partial differential equations, some of which I've shown you through simplifications already. But we can't solve those analytically, at least not, maybe if ChatGPT could, but it's not clear that that's even possible either. It can only complete sentences. It can't actually do more than that. So what has climate physics done? Over the last multiple decades, we've built physical models of the Earth's climate system, okay? This has been one of the most important advances that we've made to science generally. And why do I say that? What justifies me saying that this has been such an important advance? Well, I will put forward as an argument the justification that in 2021, half of the Nobel Prize was shared between two climate physicists, one of whom is Tsukio Manabe, and his contributions in particular were for the physical modeling of Earth's climate and reliably predicting global warming. And so with his colleagues at the Geophysical Fluid Dynamics Laboratory at Princeton University, they built a hierarchy of climate models that predicted, 40 years ago, things as follows, that the atmosphere in the lowest layers would warm, but the atmosphere in the upper layers, the stratosphere, would cool when you increase CO2. The models they built also predicted that the Arctic would warm faster than any other place on the globe, and that the land would warm more than the ocean. And all of these things have been now observed in the record, and that's obviously what underlies the reliability of predicting global warming. So we've had many successes in the realm of climate physics and climate modeling, but these models also have a lot of uncertainties. And that continues to be a challenge for us as we push toward, very detailed regional measures of climate change. Because while the models, underlying them, they are built on well understood physics, when we numerically discretize them and when we integrate into the future, we confront a number of uncertainties. Yeah?
Sorry, I'm still thinking about the previous.
Sure.
So is the jet stream in the northern hemisphere, circulates one way and the southern hemisphere the other?
No, it's the same direction in both hemispheres.
The gradients are, pressure gradients are in opposite directions. They both go north and south pole, so that doesn't that.
But you have to think of the rotating platform has changed. So in your southern hemisphere, you're standing on your head, and now you're rotating clockwise. And that flips the sign, even though, as you said, right, the southern pole is colder than the equator, and that accounts for the fact that then those two things combine to give you the same eastward moving jet stream in both hemispheres. So, yeah. Yeah, they move eastward in both hemispheres. And, right. So to get back to the uncertainty, the real issue here is when you discretize the equations numerically, you truncate the equations, and you have a closure problem, which is to say there's small-scale physics that is not being numerically integrated, and you have to represent in order to time-step the physics that you can represent on this grid. And even if we could, close this problem with a high degree of accuracy, we still face the problem that that model of closure will depend on parameters for small-scale physics like clouds and convection. That's a very difficult thing for us to observe. Clouds span length scales from microns, when we have the condensation nuclei, all the way up to thousands of kilometers as convection grows into large complexes. So we always will face uncertainty, and a lot of climate physics is dedicated to doing a better job here and reducing this uncertainty. But we also face issues with respect to initial conditions. The climate system is noisy, just like weather, and we need to sample those initial conditions to understand how that impacts our climate projection into the future. And so work actually done here at CU Boulder with Professor Jen Kay's group in collaboration with NCAR has made a lot of advances on this. They took an approach very similar to weather forecasting, where they have many simulations with slightly different initial conditions to create an ensemble that helps us to reduce the uncertainty associated with that climate noise. And then finally, we have scenario uncertainty, which is highlighting here that the climate forecast problem or the climate prediction is a boundary value problem. We have to give the climate model based on physics the CO2 concentration as a function of time. And that's something that's very hard to predict because it depends on humans and socioeconomics, and imagine trying to predict that. So there's many different pathways that we can evolve on in the future, and the models, of course, can't sample all those with finite computer time. And so this sort of leads to some words of wisdom on the use of climate models that I really agree with, and these are from Jeff Vallis, whose textbook I cited for some of that introductory material. There's really two opinions. The first opinion being that these global climate models, or GCMs, that we developed, they're one of the greatest advances, as I've said. They shared part of the Nobel Prize. We should really acknowledge them and lift them up. But on the other hand, these models have so many uncertainties that we need to be very careful and not trust them unless we can back-end that simulation with an understanding, a mechanistic physical understanding of what emerges from the simulation. And he also highlighted that the two climate physicists who were awarded that part of the Nobel Prize in 2021 were really exemplars of this philosophy. And so we can think of this as a gap that we need to close between just simulating the answer, which is very easy to do nowadays with powerful computers, but as we all know, garbage in equals garbage out. So we want to not just simulate, we want to understand. And so what I'm going to do for the rest of the talk now is use this problem of the jet stream into the future and try to do both, right? Try to theorize and think through how the jet stream might change, look at the emergent behavior in complex simulations and sort of show that that emergent behavior, what underlies that is some robust physics that we understand. So the starting point is to go back to this diagram. We laid the foundation that we understand the jet stream as this dominant force balance in latitude and height, and that it's eastward moving aloft. And so the question becomes, how does climate change impact this picture? And we can make an argument, as I'll see, intuitively, we might expect that climate change makes this tropical region on the left warmer and lighter. And so what justifies that intuition is that a key process that affects both the temperature and the density response is the presence of water vapor. So the presence of water vapor in the atmosphere, which is dictated by this Clausius-Clapeyron relation, tells us that the water vapor saturation specific humidity, the amount of water vapor in the air in kilograms per kilogram of air, is a nonlinear function of temperature. So this nonlinear function is a phase curve that if we take the Earth's global average temperature and we move up, this is the maximum amount of water vapor the air can hold at that temperature. Now what happens if we warm the climate by, let's say, a delta Ts here of 4 Kelvin, I just moved it to the right, then clearly we can see that warmer air holds more moisture. Now this has two effects. One, water vapor, whose molecular mass is 18, is a lot lighter than dry air, which is predominantly oxygen and nitrogen. So we make the air lighter when we add more moisture, but in addition to that, when we add more moisture, as the air rises up, when it contains that more moisture, it will condense and release that latent heat aloft when it condenses out to liquid. So we both warm the atmosphere in the tropics aloft and we lighten the air. So that's two dominant effects that we can expect in the tropics. But of course, the jet stream picture we've built is not just about what happens in the tropics, it's about that contrast of the density of the fluid between the equator and the pole. So let's look at now revisiting this picture, but with not just a single temperature, but the temperature contrast between the pole, which is obviously very cold, and the equator, which is much warmer. When we warm both of these quantities equally by 4 Kelvin toward the right, we see that what happens because of this nonlinearity is that the gradient increases, and that's because moist regions or moist air gets moister. And so if it's an increase, I should have said, this linearity of this, the linear slope of this curve is 7% per Kelvin. So if we've warmed by 4 Kelvin, we have a 28% increase. But it's 28% of what you start with. So over here, it's very cold. You don't have much water vapor. 28% of a small number is essentially small. Whereas over here, you've got a very warm and moist atmosphere. 28% of that is really large. So you get this clear steepening that is even independent of temperature changing between the equator and the pole. This is just a uniform increase of temperature that we've applied. Yeah?
You mentioned sort of the fact that water vapor is lighter.
Yeah.
Certainly that's an important factor.
Yeah.
But the heat capacity is also much higher.
Mm-hmm.
So how does that influence, adiabatic expansions and things like that?
Yeah, so that more has to do with the storage capability of the atmosphere, which is a transient effect. So we're really thinking here about the steady state, but you are right that the atmosphere can store more energy if it has more moisture.
But basically it's not important. It's not as important.
That's right.
Molecular weight.
Yeah, exactly. So we can then now justify that this picture, without much change over here, we expect the maximum steepening to occur because of the nonlinearity, and then just translating that to the force balances, we expect this acceleration, that fast winds or jet stream winds will get faster. So that's sort of the understanding part, and now we want to go to the simulations to see if this emerges when we take the most complex state-of-the-art simulations. But we have to do a little bit of due diligence because we saw all these uncertainties, and we want to make sure that the models can actually capture what we see in our best known state estimate of the jet stream strength. So that's what's shown here. The dashed line you've already seen, and the model average is in black, and the shading across different models, because there's many climate models around the world that look at future climate change. And so it's actually really good agreement for the average here. And when we look at the future, at the end of the century, so 2080 to 2100 relative to today, now looking in the percent per unit here of global mean warming, we see a very robust response where the jet stream is 20 to 60 degrees. So the models suggest in the future that the average jet stream wind will get faster. And the rate of this increase is 2.6% plus or minus 0.9, which is the spread over the models per Kelvin. So we're interested in the average, but I also argued that some of the impactful aspects of the jet stream for severe weather really project onto the fastest winds. And so we can also look at those fastest winds. And how do we quantify them? Well, we can define a threshold based on a percentile of the distribution. So at each latitude, we take all longitudes, all days, and we take the 99th percentile of the distribution. And then we can look in the models, which again is the thick black line with the spread in the shading, and then the best known state estimate of observations, which is the dash. Now, here I've had to coarse grain the observations because the models are quite coarse, and to make a like-for-like comparison, that's really important. So the models do equally well for the average jet stream winds as the fastest jet stream winds. And what's remarkable is that the percent increase when we look into the future is also quite similar. Across the 20 to 60 degree latitude range, we're also talking about on the order of 2%. So this is some kind of magic number that we would like to be able to physically understand, but for now we're just documenting what it is. So if the average increases at 2% per Kelvin, getting faster, and the fastest winds on average increase at about the same rate, this implies that the wind distribution is changing. And so if we look at now for all percentiles, the change of the wind relative to the average denoted by the overbar for the same future minus past time period, it's showing that the fast winds over to the right increase substantially more than the average winds by up to 2.5%. Okay, so this is not just a shift of the distribution, it's actually fundamentally changing the distribution.
But is it just like rescaling the whole thing? Because you said it's like 2%.
That's right.
Okay.
So that's right. It is still 2%, but just like for the moisture response, it's 2% of what you start with. So if you're talking about a 75 mile per hour winds, it's 2% of that is much larger than the average, which is about 30 meters per second, not miles per hour. Yeah.
What was the original asymmetry between the southern and northern hemisphere?
For the jet stream, or
The jet stream.
that's a whole other talk. But we have a paper on that.
But what is it like the leading
There's two leading factors: topography, that just disrupts the jet stream, and you can imagine also friction. And then the other, symmetry breaking between the hemispheres, is not the surface heat capacity we showed. It's actually that the ocean is moving energy across the equator. Anyway, so that's a whole other talk. But yeah, there are asymmetries between the hemispheres that can explain the jet stream asymmetry. They're not exactly the same. Okay, so we've got this understanding, we've got some emergent signal in the models, and the objective now is to tie them together. The first due diligence we want to do is that, is it the case that this get faster signal is robust? Namely, if we simplify the physics in the model, does it still emerge? And so we're used to doing this in climate physics using what we call the climate model hierarchy. This is a hierarchy, it's not the hierarchy. But what we're envisioning here is, having looked at the state-of-the-art climate models that show this emergent behavior of fast jet stream winds getting faster, and intuitively we think this might have something to do with moisture, that it doesn't depend on ocean currents. So we can simplify the model by removing the complexity of the ocean currents and just have an atmosphere model where we prescribe the ocean sea surface temperature. And what really matters is that we warm the ocean to have that moistening effect. And then we can also envision, well, none of what I think matters is anything to do with land. That's also very complex. So let's remove that and look at what happens in a water world in an aquaplanet world. So this is sort of hinting at if we can get the robustness across physical complexity, we're getting toward hopefully, uncovering the physics that underlies this that may not be, very complicated. So the first thing we do is remove the ocean currents or coupling to the ocean. We just warm the sea surface temperatures everywhere by 4 Kelvin, just like that thought experiment we did. And we see a very robust behavior in these jet stream latitudes, also around 2% per Kelvin. So that sort of green lights that the physical complexity that we have in the ocean over here is not necessary for this signal to emerge. Now what happens if we go to an aquaplanet, just a water world, no land? We also see the emergence here. The shading is well outside of zero. It has a lot more structure, and that's well understood to be some of the biases in the aquaplanet. The jet streams are much too fast there. And when we warm by 4 Kelvin, however, we do see the behavior nevertheless. So this, again, shows us that the signal is very robust. And so we don't need to throw everything into the kitchen sink into our model to get this behavior to occur. It's more likely than not related to some straightforward, underlying physical mechanism. And that mechanism that we want to pursue now and really, close the circle is to show it has something to do with what we argued before, that under global warming, the tropical regions get warmer and lighter, and then we can use that to understand the 2%, and then, that consequently allows us to understand the increase of the fastest winds. So the rubber hits the road now. I have to show you a little bit of math. So how do I show the simulations have this emergent property is I need to show you that the diagram can be written out, the force balances can be written out in mathematical terms. And then I'll use the simulations to show that when I look at the balances in the simulations, the same physics emerges. So what thermal wind tells us is that the vertical structure of the wind, so how the wind varies with pressure in this case for altitude, these are partial derivatives, is related to the density here through the specific volume alpha, weighted by the radius of the Earth and this Coriolis parameter f that depends on Earth's rotation. Now if we're interested in the winds and explaining the winds, we want to integrate this equation from the surface pressure to that jet stream level, the one we've been using, 200 so-called hectopascals. And that means we have to integrate this density contrast over that layer. Of course, our intuition is telling us that this wind response has to do with moisture. So now we need to follow previous work by Carrie Emanuel, who essentially said, well, you can reveal the dependence of this thermal wind on moisture by writing the specific volume, which is related to the inverse of density, and make it depend on 2 thermodynamic variables, pressure, and this is saturation moist entropy, which is an entropy variable that's conserved even under the phase change of water. So even if we have water vapor changing phase to liquid water, this thing is still conserved. It's not conserved if we have the phase change from gas to solid or liquid to solid. It's not conserved for that ice component. But this is exactly what we want, because this underlying what this represents here is that Clausius-Clapeyron relation. It depends only on temperature, and if we follow through the thermodynamics, we can write this gradient with respect to latitude using a Maxwell's relation as the product of 2 effects. One is how temperature varies with pressure. If we fix this moist entropy, which we call the moist adiabatic lapse rate, so how temperature varies with pressure and how condensing water releases heat that shapes how fast the pressure decreases with height. And then how this moisture and temperature vary with latitude is this additional term. So the first thing we want to assess is whether this quantity, which we've just derived, has anything to do with the signal we're trying to explain. So when we look across those climate simulations, and the signal we're trying to explain is on the y-axis, which is this fast winds and how they change in percent per Kelvin, over the 20 degree to 60 degree latitude range. And then we look at this, our moist thermal wind, which we also look in the same region for different models, which are different symbols in the different hemispheres with closed and open symbols. We see a very good correlation, which says that while there are other factors that shape the jet stream, under climate change in the future, this thermal wind has a lot to do with it. So what we can do now is use this thermal wind decomposition to reveal how the nonlinearity of the moist get moister response of Clausius-Clapeyron might relate to the fast jet stream winds getting faster. So what we do is we take our moist thermal wind variable, we take a climate change, which is this delta notation. Now we have to apply that to the integrand, which is a chain rule. So we have two terms. The first is the change of this, how temperature varies with altitude or pressure, multiplied by the latitudinal part staying the same. And what underlies this term is what we've already described, that if we think about what happens when we warm the climate and we add water vapor, we expect that there will be heating aloft because the warm and moist air will be moved upward and it will condense and release that latent heat aloft. So this is a stabilizing effect because you're warming aloft where it's cold. And so in fact, we don't expect this intuitively to be the source of the fast get faster response. This is a negative impact on the temperature vertical structure. And so it should actually decelerate the winds. But we'll get to that in a minute. And so the second contribution of the chain rule is how this latitudinal, what is going on with the change of this moist entropy with latitude. And this is where the Clausius-Clapeyron comes in. There's two contributions here. One is just a dry entropy, which depends only on temperature, so it would require a change in the temperature contrast between the equator and the pole. And then the second contribution depends on this Clausius-Clapeyron Q star that we've highlighted and argued that because of the nonlinearity of the Clausius-Clapeyron relation, we get this steepening of the gradient that would happen even if temperature were changing equally everywhere, which we call uniform global warming. So what we're now going to do is apply those two terms to see how we can explain this 2% per Kelvin of change of the fast jet stream winds. So if we look at the blue term, which is the impact of climate change on how temperature varies with height, the so-called moist adiabatic lapse rate, that's indeed a decelerating contribution because you're warming where it's cold, which is opposite, and so it's a deceleration. And so this tells us fast gets slower. This is not the signal we're looking for. Now the other contribution, which is the latitudinal change of the moist entropy, is clearly in the right direction. It's very flat, but it's an overestimate. And that's because it's the sum of two contributions, the part that was dry and dependent on temperature alone, and then the part that was dependent on moisture. And so we can separate those. And in particular, if we just zoom in on the part that depends on this moisture variable, we get really close to where we want to end up, which is this 2%. But encoded in here when we calculate it is in fact a hidden temperature dependence. I didn't highlight it here, but there it is. And so we can further remove that to really zoom in on this mechanism, which had no temperature contrast between the equator and the pole. How can we do that? Well, we can just take the global mean warming that these models predict and apply it at every latitude, okay, weighting it properly with the spherical nature of the Earth. And so underlying that is no change in the temperature gradient. It's just purely any nonlinearity that arises as a consequence of the Clausius-Clapeyron relation. And so that's the true test of our understanding that we expect, and that's exactly what we get for that calculation. And again, when we zoom in on the jet stream latitudes, 20 to 60, averaged over both hemispheres, this is basically 2%. And so what it says is that the Clausius-Clapeyron nonlinearity itself, averaged over in this layer from the surface to the jet stream altitude, can explain this rate of increase of 2%. And it furthermore can explain this change in the distribution, which is shown here again, you've seen before with the percentile and the wind response relative to the average. And how we can explain that is just to apply the same decomposition. And if we take that Clausius-Clapeyron nonlinearity and we calculate the implied change in the wind, we get up to the just over 2, factor of 2 increase of the fastest winds relative to the average, which is again all because it's 2% for all of the percentiles, but we're applying it to the wind speed that we start with. So that's the bulk of the results of the talk. I just want to take a moment to kind of summarize where we went, where we started, and where we ended up, and then I'll be happy to take questions. So the main takeaway message is obviously the title, that fast jet stream winds get faster under climate change, and I began the talk building for you a physical model of what controls the jet stream, why does it exist, the force balances in the vertical and the horizontal led us to show that that's the reason the jet stream exists, and if we envision climate change having this particular impact of making the tropics warmer and lighter, we would expect that the jet stream would get faster. And the physical intuition that underlies why this region would warm and lighten near the equator more than the pole comes from this moist get moister nonlinearity of the Clausius-Clapeyron relation. So that, of course, was just the physical intuition or theory that we then went to the state-of-the-art climate models and looked at what emerges under climate change for these fastest winds. We found that across the extratropics, the fastest winds get faster at this particular rate of 2%, what we wanted, of course, to explain. We showed that if we didn't, consider just the most complex simulation, if we started to strip away complexity, we got the same signal to emerge. And so then what we wanted to finally show was that if we looked at the simulations in more detail, the reason this signal emerges is because of this physical picture that we built. And in order to do that, we applied this mathematics of the moist thermal wind. We applied it to the models, and we took this very strict limit of having no change in temperature contrast between the equator and the pole, just global mean warming as we envisioned in this thought experiment. And what we found was when we applied that change, which underlying it is again the moist get moister response, we could capture this emergent rate of increase, which we also showed implied that the fast winds would increase substantially more than the average. So this is the story to date. There's many things we're interested in looking at in more detail, including, as a function of longitude, as a function of time. A lot of questions in climate change also prompt us to look not just at the end of the century, but today. What are the changes we're seeing today? We just started the talk with that image of the record-breaking jet stream wind. Looking at how fast winds are changing is something that we're actively doing. And so there's a lot of work to do in climate physics, and I look forward, to your questions. Thank you very much.
Yeah, I'm wondering, did you describe this latitude variation in the jet stream? Why is it undulating?
You mean north-south?
North-south, yeah, exactly. Away
Yeah.
from the equator.
Right.
Like you would have thought it would get some laminar, well, it is laminar probably, but it's undulating.
So that is not something that I talked about in detail in the talk. So the picture I built of the thermal wind regime had nothing to say about the role of north-south motion or up-down motion. Now those two things do play a role in transporting momentum. In particular, the north-south motion, when we look at the jet stream, it can become unstable. And it can lead to wave-like motion that transports momentum around. And it turns out that that can also drive a part of the jet stream. But from the perspective of this fast get faster response, that's not the leading order physics that explains it. So I didn't get into much detail
But if
about
that
it.
pattern goes and it's undulating.
Oh, it undulates.
Changing the time.
Yeah, and there's a lot of open questions. We talked about at lunch with the graduate students. Arctic warming more than the poles, which I didn't also get into. There's hypotheses out there that makes the jet stream fluctuate more. And so a lot of people in climate are trying to test that and see if the signal has emerged in the noise of observations. And I think the jury's still out. It's a very noisy wintertime signal to try to find that signal. It's very noisy. Yeah.
Thank you for the great talk, Tiffany. I was wondering, have you looked at the subtropical versus polar jet changes in the theory respective, like when the Hadley cell is expanding and the subtropics are drying out further north versus the Arctic amplification influence on the polar jet? And how does that influence the speed? Yeah.
The short answer, so there's two parts. One, the part of looking at the regional structure of this result is where we're going to examine the regionality. You also mentioned the Hadley cell, which also involves north-south motion and up-down motion that I wasn't presenting as part of this thermal wind regime. But we have a separate paper where we argue that this moist get moisture response, when you apply it to the low-level winds, which can be used to define the edge of the Hadley cell, because the winds, we have the tropical trade winds, which move from east to west, and then there's a nodal point, and then there's the winds that move from west to east. And so when you apply this entirely similar kind of arguments to the low-level winds, you also predict an expansion, because the strengthening of the jet stream goes along with the strengthening of the trades in this mechanism. And so you would expand the trade wind region, which would be like an expansion of the Hadley cell, or the tropical circulation, as we call it. So yeah, there's a lot of, I think, interest in trying to push our understanding of climate change using what I would say is the most successful starting point today, which is Clausius-Clapeyron. Land warming more than the ocean, that's Clausius-Clapeyron. Having warming aloft in the tropical atmosphere, Clausius-Clapeyron. And so this is, our attempt in my group to push that forward with respect to the wind patterns, which hasn't, that connection has not received as much attention. But clearly climate change impacts moisture in a really fundamental way.
Yeah, and this is probably a hard question to answer, but if we have, let's say, 2 degree Kelvin increase in temperature, we're trying to maintain no more than 2 degree rise, which we probably won't be able to reach. And energy goes as, let's say, certainly the square of the wind velocities and whatever. Is there, and we of course have dispersion, right? We've got some spread in these predictions. Is there some way of having some guidance as to just how important 2% per Kelvin is? It sounds dangerously high to me, but I'm not sure that I have any way of really understanding how important that is.
Yeah, so you can do a number of practical things, which is to say, if you look at whatever milestone, 2-4 Kelvin of global mean warming, can you quantify the impact on transatlantic flight times? And so a colleague in Reading, Professor Paul Williams, has done that calculation and has shown really clear substantive impacts on transatlantic flight times. People have also, like Paul, have looked at this clear air turbulence. There's implications here for the shear of the jet stream. So even at 2 degrees Kelvin, these are signals that need to be factored in a variety of ways, depending on what particular impact you're looking at. So I think from a climate physics perspective, we're trying to give reliable information. And by what I define as that is, yes, there's an emergent signal in a simulation. Ideally, many simulations show the same thing. And then we have physical understanding to say why. And it's those signals that we can justify, policymakers taking seriously and then planning. There's many signals that are very uncertain. And so this doesn't apply to everything coming out of climate models. And I think this is really where the closing of the gap is important for reliable information.
Yeah, here, Mike Dobson.
I'm just curious about your instrumentation. How are you getting this real-time data of the streamlines here? jet stream, yeah.
Like at the beginning of the talk with that.
Well, yeah, the background here shows
Oh, yeah.
streamlines. So is that data or is that simulation?
So that's this thing I called reanalysis data.
Huh?
We call it an observational product. It's very hard to directly measure the winds.
Yeah,
via
that was my question.
satellite.
How do you measure the wind?
It turns out ESA, or the European Space Agency, has a mission that's trying to do that.
I see.
But the data on that picture are not direct
I see.
observations. So just like your weather forecast you look in your phone, it's based on initial condition, the model integrates the physical equation, and it constrains it by the next observed data point through data assimilation. So what we do with those data is you do that retroactively all the way back to 1980 to the present,
I see.
and we get these products that are best known state estimates, and different meteorological agencies
Right.
produce different projects. So there's some slight, spread, but it's much smaller than our model spread.
Right, but the airline pilots can't like go to a website and see what the winds are right now.
Well, they
Yeah.
use the forecast products.
Uh-huh.
They use these products for sure. Yeah,
Uh-huh.
when they
Okay.
plan their flights. Yeah, as well as direct measurements on the aircraft, which is actually how they avoid that rough air, or they try to. They have radar measurements, and then they try to navigate around those signals from the radar that show the clear air turbulence.
So one kind of exciting thing about this talk, or maybe scary, depending on the way you look at it, thing is that distribution is changing. Right now, like we have a lot of weather models that, are statistical and trained on some distribution. Like, you expect over time with more observation, we get like a better model. But I guess in the situation of like a changing climate, should I expect the weather forecast to get worse over time? Because this like underlying like distribution of wind speeds is changing.
So weather forecast models are also physics-based, so they're not statistical. They do combine some statistical aspects, and then there's a forecaster who ultimately produces the forecast. But it's an interesting question on how forecast accuracy and predictability, going out to 2 weeks, which is the farthest you should ever look at a forecast, and even 2 weeks is pushing it. But that's definitely a research topic, right? It's a very different kind of problem. It's an initial value problem as opposed to a boundary value problem, which is what the climate simulation is. But the laws of physics are in there, and so given the right initial conditions, and typically also they initialize with sea surface temperatures, the model should capture that. But we're seeing things like this Pacific Northwest heat wave that occurred in 2021, which people have claimed is a 5 sigma event, even though it's not a Gaussian distribution. And so that's really like, pushing the distribution super far. And these types of out of sample, like really far outside the distribution events, is where you need a physics-based model. Because a machine learning or statistical trained algorithm is not, as you said, is not going to be able to extrapolate with fidelity, that far out of the distribution. And so climate change, is a real difficult thing for the machine learning community to crack. There's a lot of people who are really, pushing it as far as they can, but it's a challenging thing with these out of sample changes that we are projecting with physics-based models.
What does the faster jet stream do to the amplitude of Rossby waves and pushing cold air south and warm air north?
So yeah, that's a very good